Unit 2 Chemistry, Chapter 20, Part 3, Calculations for Volumetric Analysis. Okay, so we've gone through all this process, we've got our results, we got concordant results, and we found the average of our three concordant results was 18.97 mil. We added the 20 mil aliquot of our standard solution. Okay, so this is what we put into our conical flask from our pipette. Our unknown, our hydrochloric acid, we put into our burette. Okay, so we start by writing our balanced equation, and we find that our standard to our unknown, we have a 1:2 ratio. And I do recommend drawing up this kind of table. It can help you keep things settled and organised. We also put in what we know. So we know the concentration of the sodium carbonate. We also know the volume of the sodium carbonate, and we're going to convert that to litres, remember, because we're going to be working in moles per litre. The other thing we know is the volume of our hydrochloric acid. We don't know its concentration. That's what we're going to try and work out. And to do that, we're going to need to know the amount in moles, so we're leaving a row for that as well. So, from this concentration and volume, we can then find that amount in mole is C times V, so we can find the amount in mole of the sodium carbonate. From the amount in mole in the sodium carbonate, we can use our 1:2 ratio. So we can say, if I've got 1 mole of sodium carbonate, I've got 2 moles of HCl. So I'm going to double the amount in mole of sodium carbonate, and that's going to give me my amount in mole of HCl. Okay. Once I've then got my amount in mole of HCl, I've also got its volume. So from there, now I can work out the concentration. So concentration is amount over volume. So I take this amount in mole and divide it by this volume, and that gives me my concentration of HCl. The final thing to consider is how accurately, or how many of the numbers that are on my calculator, I write down. Okay? To do that, I need to think about something called significant figures. So what is significant? Well, a significant figure tells you basically how accurate the number is. Okay? So if I look here, this number here has got 1, 2, 3, 4 significant figures. This is not a significant number. A 0 in front is not significant. Okay? A 0 behind, however, is significant. The reason is that these zeros in front, they're just telling us how big the number is. Okay? We could express this as 2.000 times 10 to the negative 2. So then we've got rid of these zeros in front. Those zeros at the back, they've got no business being there except for to tell us it wasn't just 20 mil, it was 20.00 mil. It's giving you information about the accuracy. Okay, so this one is significant because all integers are significant, and all zeros after it, if they're after a decimal point, are also significant. So that's also 4 sig figs. And this number here is also 4 sig figs. So they're the 4 numbers that we were given in our question. Okay? So zeros within a number are significant. Zeros to the left of the first non-zero, the first integer, are not. And generally it's easier to do that to put it into scientific notation and say zeros which are after a decimal point, which have got no real business being there other than to tell you how significant they are or tell you how accurate it is, like these, they are definitely significant. The ones which are a bit ambiguous is when you've got zeros which are telling you, could be telling you how accurate it is, or could be telling you just how big the number is. So if you've got 5,500, if you want to express that to 2 sig figs, you would use scientific notation and you do 5.5 times 10 to the 3, because that's definitely 2 sig figs. If you want to express it to 3 sig figs, you'd do 5.50 times 10 to the 3. This is a bit ambiguous, so scientific notation will help you out there. When we round mathematically. Okay, So if the last number that is going to be dropped is equal to or greater than 5, you round up. Okay, so 1.655, we're rounding it to 3 sig figs, so we're cutting it off there. That first number that's going to be dropped, that's 5, so we're rounding up, so that becomes 1.66. Whereas 1.652, this is the first number that's going to be dropped. It's less than 5, so this one we round down. Now, the degree of accuracy that you can express your answer to is always going to be the same as the lowest, most accurate one that you used in your calculation. Okay? Now, depending on what calculation you're using, depends what you're doing. So if you're just adding and subtracting, like with the titers that you're doing, so when you go from your initial volume and your final volume to find your titer, that's a subtraction. So there we use the same number of decimal points as we had in it. So for your ret, that would always be 2 decimal points, so your answer should be 2 decimal points. If you are multiplying or dividing, which is for most of our calculations, then we are looking at the number of significant figures. So here, this bit of data's got 2 sig figs, this one's got 3. If we multiply them together, the answer that will come up on our calculator has got 4 sig figs. But we can only be as accurate as this piece of data here was. So our answer is going to be 0.36, because our answer has to be to 2 sig figs, because that's our least accurate bit of data. Okay? The other thing that's worth bearing in mind is that whilst you would round it like this when you write it down on your piece of paper, you would keep the full number on your calculator. Otherwise, you're going to get rounding errors creeping in. Okay? So a little error where you've rounded in step A, by the time you get through to the last part of a question, can have a big impact.